My name is Steve Skiena. I'm a professor at Stony Brook University, and I'm going to talk to you today about some work we're doing on turning features into graphs. And again, I'm an academic. Some people may be familiar with some of my books. Do we have any algorithm design manual fans here? A few people here. Okay, good. So again, I'm interested. I've been interested in classical graph algorithms for many, many years. Over the last 10, 15 years, we've been interested in data science in various dimensions. And the work I'm going to talk about today, and which is I think going to be what's interesting to you guys, is kind of a combination of the idea of graphs and how they apply in data science. And in particular, let's just see if this works. Okay, yes. So what I believe is, if I understand who you guys are, you're a different crowd than I usually speak to. But I am going to say that a large fraction of the people in here have graphs that they work on, okay, as data in some way or another. And I'm imagining a lot of you guys want to build models to use this graph to get more out of it. You want to build probably some kind of a machine learning model or a predictive model to learn something about the vertices of your graph. Perhaps you want to do something like linear regression or SVMs or deep learning or anything. You have a task in mind. Maybe you want to predict two nodes that are going to be connected to each other. Maybe you want to classify, oh, here's a node. Is it going to be interested in this product or not? Maybe you want to do some functional prediction on it or regression, okay? And typically what I believe you guys have is you have a graph, you have some attributes of each node, so some features you could build a model on. But somehow there's this graph still, and you'd like to get the topology of that graph into your model. And what I'm going to be talking about is something we developed called DeepWalk, which is an amazingly simple, okay, unsupervised approach to taking your graph, crunching on it for a while so that we build features, okay, such that these features are going to be useful for any kind of a machine learning model you're going to be building. And that's kind of what I'm going to be talking about here. So as far as the outline here, okay, our technique for DeepWalks depends on something called word embeddings, which many of you I think have heard of. They were mentioned earlier in one of the early talks. I'm going to show how our idea is based on word embeddings. And to get at the heart of why word embeddings are interesting, okay, I'd like to say, suppose you wanted to represent the concept of cat in a computer. Okay, what is the most useful representation of cat? Okay, maybe it's the picture, you might say, or maybe it's that definition over there. Or I guess being graph people, you probably want some knowledge graph about graphs and stuff like that, and you say, yes, a cat is a node in a knowledge graph. For our purposes, do I have a clicker, pointer here? No. For our purposes, what a cat is going to be this vector. And I want you guys to look at that. What we do have it. Okay, very good. On top. Okay, is that true? Very good. Okay. So what I want to convince you of in here is that what a cat really is this. And if my talk is successful, you're going to be able to look at that and say, sure, that's a cat. It looks just like a dog. Okay? What is the point now? Okay, let's keep moving on. So what is the idea? The idea behind word embeddings, and by word embeddings I mean word to vec, which is I'm sure a buzzword people have heard of, is that you'd like to be able to take a large amount of text that you know nothing about, no annotations, just being text, and try to figure out what the meaning of words are, what the roles of words are. And the idea that lurks behind word to vec is that if you know what words mean, you should be able to tell the difference between a real phrase and a corrupted phrase, okay? So if we take a look at some text, a perfectly reasonable thing to have in your text is when I visited New York, okay? That might have been in a text corpora that you had. Suppose I now want to corrupt it. I could take the middle word and randomly change it. Pick a random word from the vocabulary and replace it. And unless you're a really terrible writer, taking your text and replacing one of the words at random will make it worse, okay? So the great thing about this idea is you can take a large amount of just positive examples, automatically construct negative examples, and if you can build a system that is good at telling, given the choice of a original phrase and a corrupted phrase, if you could figure out how to tell them apart, you must know something about what the words mean, okay? And this is basically what word2vec does. Oops, sorry about that. This is what word2vec does, okay? There is a neural network that they use, but exactly how that works or so is not really important. What is important is that basically it treats each word as a vector, okay, of 64 dimensions or 100 dimensions or 128 dimensions, okay? The neural network is exposed to pairs of real and corrupted things, okay, and it adjusts its weights and adjusts these representation vectors so it gets good at separating real phrases from corrupted phrases. And once you do that, you've got a sense of what these words mean, okay? And again, I told you that you were going to be saying, why does a cat look like a dog? Well, if you build these things, this is kind of like a visualization of some word embeddings of popular words. And if you look at them, sure enough, if you look at the vector of values for a cat and dog, they look very, very similar. Certainly you could tell an animal from a color. Does everybody see the pattern for colors looks different? And numbers and countries, okay? And so you can view that what we have done is we have trained and built models where there are, in this case, 64 dimensions. We don't know what the dimensions mean explicitly, but it's clear that they capture the similarities of what words mean. Okay, and that is the underlying technology for word2vec, and that is going to drive our graph feature representation. And again, these word2vec things are really kind of amazing when you start to play with them. So if you take a look at some of these things and you say, treat each word now as a point in 100 dimensions or so, you can ask yourself, what are the nearest words to it, okay? And these things are often really uncanny. For a country, the nearest words are going to, oops, I'm sorry about this. This is difficult for me. Countries, nearest words are going to be other countries, and other countries in the same part of the world. Colors are going to have their nearest neighbors as colors. Okay, dentists are going to have their nearest neighbors as orthodontists. Okay, and it's smart enough to pick up on the difference between capitalized and lowercase. Lowercase apples are fruits. Uppercase apples are companies. Okay, any questions about that? Oh, maybe we'll save that maybe for the end. But the key point here is that you can capture all this similarity learned in an unambiguous way from text. And this is actually an example, you guys like graphs. We took all of the English words, we developed what their representations and points were, connected words to their nearest neighbors, and now you've got a network, and now you can project it and cluster it and things like that. And there's amazing clusterings that you see in here. You know, like these are last names clustered differently than first names, and cities clustered differently than states, and all this kind of stuff. So this kind of unsupervised thing does an amazingly good job of capturing what is interesting, what is going on, just given a large body of text, okay? And again, in our lab, we work a lot on language processing. We've done all kinds of things that we find interesting with these kind of embeddings. One of them, we've built multilingual entity recognition systems. Polyglot is a system we built that can do basic NLP in 100 different languages. And the reason we can do this is we trained on Wikipedia editions from all of the different languages. And from that, we could leverage it. And again, the similarities, the subtleties that it picks up, I find amazingly interesting. Like apparently in Arabic, there's a word for two boys. And when you look at what the nearest neighbors are, it's two sons, two children, two daughters, okay? So there's really a lot that you can pick up in this unsupervised way about what words mean, and it gives it a lot of power. Okay, but you guys are graphs people. You're not are not NLP people particularly. How can we adapt this idea of using word embeddings, okay, to graphs? And we developed a technique called DeepWalk that does that. Okay? So what would you guys people like to do? You have a graph. It's got all kinds of nodes and edges. It's got a topology associated with it. And you can represent your graph in different ways. Again, obviously, the people here want you to represent it with Neo4j. Somewhere, perhaps conceptually, you could represent it as a adjacency matrix of what node is connected to what other node. You would like to be able to take this connectivity information and turn it into features for all kinds of different applications that you would care about. So how can we do that? We developed a method called DeepWalk that is going to learn say latent representation. And by latent representation, I mean one of these higher dimensional representations where the dimensions don't really have names associated with them or features. They just kind of think about representing the vertices of a graph in some higher dimension, typically 100 dimensions or so, okay, so that we can use these dimensions for features. Okay, and what is great about, we have a DeepWalk algorithm, which I'll tell you exactly how it works in a minute, but what's great about it? What's great about it is it tends to be very scalable. There are other techniques that some of you may know from linear algebra, like SVD, singular value decomposition, or something like that, for taking matrices and turning them into features. This turns out to be a very, a complicated and expensive operation on very, very large graphs, okay? DeepWalk has the property that we don't need the entire graph at once, which you need to do in these kind of matrix methods. We can work online with it. As chunks of the graph come in, we can do something with it. And it has become very popular. It develops very, very good features. And the connection with what I said before is that it works on an analogy with natural language, okay? In particular, if you think about if you have a vocabulary in a language, what are sentences? Sentences are sequences of words, okay? That's what a sentence is, okay? And what is a walk on a graph? If the vertices of a graph can be thought of as being the words of a language, then walks on a graph can be thought of as being sentences in the language, okay? And if you know about training if word2vec is this magic for taking sentences and turning sentences into features, then why can't we use random walks and turn them into, treat them as sentences for the same purpose? And that's basically the entire idea behind DeepWalk, okay? We are going to take a graph, we're going to generate random walks from each vertex in the graph, okay? Use these as training data. Our random walks are going to be short, some length, so that they are analogous to sentences. Well, maybe of length 40 or 20 or 40, it's a parameter, okay? And being a random walk, we are just going to take the next step from all of our neighbors uniformly as the first try. Maybe you might want to try to sweeten that in some way, but for our bread and buttered algorithm, we're just going to take random walks, visiting each neighbor, basically uniformly. And we're then going to feed this thing to word2vec, which is going to now try to build vectors out of this thing, okay? So that, and we'll come back there, so that, so that, again, word2vec is going to try to predict what vertex, given I corrupt a vertex on I randomly substitute one of the words, one of the vertices on the walk with another vertex. Can I tell the difference between that and the real walk? Okay, if I get better and better at that, I know what the words, the graphs, what the nodes of the graph mean. And that's kind of the secret to what we're doing here. Okay? And again, being academics, we compare ourselves against other algorithms, spectral clustering, things like that. Those are sort of like the SVD methods that we've been talking about. There are a bunch of methods for turning graphs into features. Here we were looking at trying to classify. This is a multi-label classification problem where we were given a graph and we had a small percentage of the nodes were actually labeled, and we wanted to figure out the labels of the rest of them. And even given a smaller fraction of the training labels, we were able to do a pretty good job of reconstructing what the labels were, and better than the other methods. That's what we like. And when you run it on very, very large graphs, some of the methods like spectral clustering, which tend to do very well, okay, you can't run them on very large graphs because they require the whole thing in memory. They are superlinear algorithms, things like that. So, so DeepWalk is able to do these kinds of things. Basically, DeepWalk has become amazingly popular. Everybody is doing the DeepWalk, okay? You can see who's somebody else trying to do the DeepWalk. You know, again, as an academic, you know, I'm a reasonably well-cited academic. I have never had a paper get anywhere near as popular as fast as this DeepWalk paper. You know, there's all, you know, by the citation statistics are extremely good. It's quite popular. If you measure, perhaps the biggest conference in data mining or data science is something called KDD. And out of the 4,000 KDD papers that have been published over the last 20 years, ours is the 28th most popular over the last year. So it's something that particularly a lot of people are reading. And again, you too can do the DeepWalk. You may say, how can I do the DeepWalk? Okay, well, we'll be talking a little bit later about how you get DeepWalk in Neo4j. But let me just give you an example of why I think this is a great method for getting data from graphs. I've worked a lot over the years in doing analysis of Wikipedia, and I'm interested in social science kind of things. We wrote a book on ranking the importance of historical figures, okay, based on analyzing Wikipedia. And one kind of question that you would like to be able to ask are, which people are similar to each other? So you can imagine that the population of Wikipedia, depending on when you do it, is 500,000, 1 million people, okay? And certain people are similar based on some kind of roles, some kind of when they were in history, what were they doing. We were interested in trying to build systems that a program that given given the context of Wikipedia could tell which people were similar to it. You would like to say who's similar to Einstein? Well, you'd like someone like Feynman and Max Planck and Newton, okay? And maybe you might think, well, why don't we do it by analyzing the text? And given that my group works in text processing, we spent a fair amount of time using our word embeddings and our text analysis to try to read the articles and figure it out. But we ended up getting much better results just using graph embeddings, okay? How do you tell whether you understand what Wikipedia are? Well, we did some tests where we took triples of historical figures and measured something about what categories, and if you're in a Wikipedia or have a Wikipedia article, at the bottom of the Wikipedia page, there's categories that people are put into. And you might say two people are probably more similar if they share more Wikipedia categories in common. And so that was one way we could evaluate whether or not our method was doing a good job. And when we did it, again, we looked at a lot of different methods. We tried looking at the text of the articles, and we tried doing topic analysis, if you know about natural language processing, LDA and stuff like that. And we worked pretty hard at trying to analyze the articles. But we found that when we just took the network of who's connected to who in Wikipedia, if my Wikipedia article cites quotes your Wikipedia article, then presumably there's a connection. And we found that if we did just the DeepWalk of the the connectivity graph, and then asked ourselves, is the DeepWalk representation of these two nodes closer than the third one? That would be the more similar one. And this did much better than all the ones we worked pretty hard on. And in some sense, it said that if you wanted to analyze Wikipedia and figure out who's similar, okay, who are the people that, capture that idea, you should throw out all the text and just read the links, okay? And that was kind of an amazing thing for us. And again, they were interesting anecdotal examples. When you look like who were the nearest neighbor of Beethoven, you got Schubert and Brahms and Mozart. Who was the nearest neighbor in DeepWalk space of Mick Jagger? You got Beatles, you got Rolling Stones, right? Who was the nearest neighbor of Obama? You tend to get presidents, you got Democrats, okay? Who was the nearest neighbor of Scarlett Johansson? Well, you got reasonably young actors and actresses, okay? Who was the nearest neighbor to me in Wikipedia? Well, okay, it was, okay, yes, sir. And the amazing thing is that 2 out of 3 of us are billionaires, okay? But the rest are computer scientists also. So I count that as a win. And if you also notice, the number in the parentheses is the distance. And as you can see, I'm further from Larry Page, for example, than Beethoven is from Schubert, okay, which captures the idea that maybe it's not quite as close a match, okay? Fair enough. Okay, and again, we've been interested in these network embeddings and these notions of historical similarity. We have an app, a way of kind of browsing similarity orders. Once you can tell that 2 things are similar, it opens up all kinds of different, in some Gestalt sense, even if you don't know what it actually is. You can kind of use this kind of thing for browsing. You find something you're interested in, you want to look at other things that are similar. And this is a way of turning your graph into some kind of a notion of similarity that I found very, very powerful. Okay, so that's basically what I wanted to say. But there's enough interest in DeepWalk in a lot of applications that they're implementing it at Neo4j. And Michael is going to take the rest of the talk and explain what you guys have been doing.
Yeah. Thanks a lot, Steve. That was really insightful. Yeah, I'm standing in for my colleague Mark Needham, who couldn't come to New York, and talk about how we used DeepWalk implementations to make them available in Neo4j. So in principle, as Steve said, basically you want to take the data in your graph and convert it into something that then can be used by machine learning methods, right? Whatever the method is, but you want to have a kind of feature vector. And also we want to enable all of you to make this as part of your Cypher workflow. So you don't want to pull the whole graph into another library, do the analysis there, and then pull the data back, and like lots of additional steps. But we want to make it as easy as possible. And it's also something you don't want to do as a manual step. You don't want to identify all the features that are relevant manually, because that is probably as error-prone as letting the algorithms do it, right? And so what we did is we built an Neo4j user-defined procedure that takes your graph data and runs DeepWalk on the graph data and then returns or stores embeddings or feature vectors on each of the nodes of your graph. So you can get this as part of currently an experimental library, but if as it kind of finishes and the stability is as where we want it to be, and as we get enough feedback, we will also move it as part into the graph algorithms library as well, so that it's then available out of the box basically in Neo4j. So currently there's an ML models repository with also releases where you can download the library and then use that. How does it implement it? We didn't do the whole neural network that Steve showed on the slide, but we basically used the implementation from deep learning for Java, DL4j, which has already a DeepWalk implementation, where you can just plug in other graph sources to run random walks on. And so that's what we did. We basically took the data in Neo4j, made it available to the DeepWalk implementation, deep learning for J, and then took the results out of that DeepWalk implementation and made it available again to the user or stored it into the graph. So it looks like this. You call just a procedure. The 2 nulls on top is basically your labels or relationship types that you want to run on, or you can even specify one cipher query that generates a node list, another second cipher query that generates an edge list, so you can also vary custom projection. So if you have data in your graph in a certain shape, but you want to run the DeepWalk on another shape of the data, like a projected or an aggregated view, or an user-to-user or citation-to-citation view, then you can project it to any kind of shape. And that's what you pass in on top there. Then you just pass in the DeepWalk parameters that you want to use and the property that you want to use for writing back the data to your nodes and run it. And then after a few seconds or minutes, it completes, and then all your nodes get feature vectors as properties stored that you then can later use for building a KNN network or whatever, right? You can take them and feed them to a deep learning network or other things. Or you can combine them with other properties like actual node properties or graph algorithm properties like centralities or clusters or things like that, and then have an even more interesting vector as well. Okay, and basically that's it. That's it. You don't have to do more, right? So it's really just calling this procedure on your data, and then it magically computes the feature vectors for you, and then you can do all the fancy stuff that Steve showed you that you can do. And so in the dev zone, which is on the fourth floor, Amy and Jake are running the graph algorithms in a ML booth. And if you want to know more, want to try it out, just come there and talk to us. Also, if you have feedback, if you try it out and run into questions or things that you want to talk about, then we'd love to hear from you and get feedback on that so that we stabilize all this stuff and get it into the graph algorithms library as quickly as possible. OK, and yeah, that's basically my thing. What we also are working on besides DeepWalk is there's another approach. It's called DeepGL that we are working on with a company called Braintree in London, which uses then multi-level and multi-generational feature reduction and things like that, which is also really interesting and that we're currently also exploring. And other things that we're also adding to the graph algorithms library is providing different similarity metrics. So you can do Jakarta similarity, Euclidean similarity, cosine similarities on top of these feature vectors to then generate the KNN network out of that. And that would be actually a question for me to Steve. What kind of similarity metric did you use to compute the distance on the feature vectors?
See, okay, so I mean,
yeah,
I can come up here. Well, so take a look at that.
I mean, should probably not use the. Yeah.
No, I think I like this one better.
Yeah.
If you want to know the truth, there you go.
Yeah.
I think that's better.
Thank you.
But no. So I mean, the question was about I guess similarity metrics. I don't remember exactly. We probably just used the Euclidean metric. I mean, again, I personally find these features very surprisingly robust, and so so it's not that sensitive to what metric to get some sensible thing of what is similar to something else. We usually use a Euclidean metric. Sometimes we use cosine similarity. That's also something we use a lot. But in general, I don't think that it's particularly sensitive to that.
Cool. Any other questions from the audience?
Yeah.
I know with word embeddings, one of the initial problems is dealing with out-of-vocabulary words. And there are some other techniques like fast text to be able to use subwords to represent out-of-vocabulary words. Do you have any equivalent if like a piece of a graph would show up, a new piece of the graph that has not been deep-walked,
Right.
deep-verified? Any techniques maybe to know what the representation of that might be without batch computing as well?
Okay, so what do you do when the question?
Can you repeat the question?
Let me try. The question has to do with what do you do? Okay, with a limitation, let's say, of word embeddings in English is what happens when a new word comes along, like Neo4j. No one has maybe trained that in the corpus that people had used. What does this mean? Okay. And there are techniques that people have developed in natural language processing to try to get around these things. That's basically what was being asked. What would I do if you now said, oh, I'm going to have a graph where, because I guess the heart of the problem here is that there's a batch training that is going on, okay? And you're given your graph, you're going to spend a certain amount of time chugging through it to build an embedding. Over time, things are going to change. You want to keep that embedding around for a while. You could, first of all, if you really have your act together, you could take your new thing and start doing, as soon as you insert it in the graph, you could start to do walks from it and maybe keep that online. But that's not the mainstream thing to do. Typically what you would try to do is impute what the embedding would be for your new thing without, in a couple of methods. One is you could say, well, look, if this node in my graph is connected to, new node is connected to 5 other nodes, and I have DeepWalk embeddings for 4 of them, maybe taking the centroid of those 4 is a reasonable estimation for what this new node that I otherwise know nothing else on. So that might be one way to do it. Another possibility is to do some kind of a regression thing where you might want to be able to, given if all you have is property, let's say you don't even have this thing in your graph, okay? You don't have any connections to anything else, but maybe you've got some metadata about what this node is. If it's a company, how big is the company, where is it located, stuff like that. Maybe you could use regression to try to take the features and predict the DeepWalk vector from the features. and that could give you a, some kind of a representation for it, okay? But, so if you've got dynamic graphs, this is a problem you have to worry about. If your graph isn't that dynamic, then of course you shouldn't have extra vertices that you suddenly have to worry about.
Yeah.
So, if I apply this algorithm to online prediction, and for example, I have 10,000 different names, I want to find a similarity that to say what's the most similar names you have. Because I think if you want to compare name by name, it consumes lots of time. And if you want to apply online, how could you do to save the time?
Okay, so
Question.
the couple of questions that may be in there. If I'm not going to get this question right, then so one question was about, I think, the complexity of finding nearest neighbors. Okay, so that if you want to find who is the most similar person to Skiena in the Wikipedia DeepWalk embedding, ostensibly you've got to go and now compare me to all the other people in Wikipedia. My embedding, which is now a 100-dimensional point in a 100-dimensional space. If you compare it explicitly to every other element, then that is now an order n computation where n is all of Wikipedia, and that is large. Well, the fact that this is a geometric thing means that there are some algorithms for nearest neighbor search or near neighbor search in high dimensions. It becomes a geometric problem, and so there's certain geometric data structures you can use to try to do that. So it is finding nearest, exact nearest neighbors in a modest number of dimensions is not trivial, but on the other hand, there are fast data structures to get you fairly close. So if the question was about how do you find nearest neighbors, I would say realize you're now living in a geometric world, and the algorithms that come from geometry are now at your service to do that. Okay? I don't know if that completely answers your question or good enough. Okay? Any other questions?
Yeah.
Yes.
So,
Yeah.
if I understand correctly, the premise of this approach is if there's a property that I don't know about a new node, but I do know the connectivity, I can get its vector, and then I can predict the property from the vector.
Right. Oh, okay, let me say it again. Okay, the question was about the reason we care about these kind of features. Why do you care about this graph feature at all? The idea is somehow that there is some subtle stuff lurking in the connectivity that you may not have explicitly in your features.
You suggested that ultimately it relates to your neighboring nodes, and I'm just wondering why not just use the network and find what the property is on the nodes where I do have it? Simple nearest neighbor
Okay.
in graph space.
So one question is, so the question is, why do you mess with this this DeepWalk stuff at all? Okay, you're saying if I want to label whether or not what I want to try to identify if this person in my network is a terrorist. Okay, and I'm going to say, well, I could look at my nearest neighbors, my direct neighbors, ask if they're terrorists. If they're terrorists, I'm more likely to be. Okay, the advantages of doing something like DeepWalk are a couple. One is that you are coming up with, okay, so first of all, recognize that a lot of your neighbors are not always going to be labeled. So let's take the terrorist example. I think I showed you some results where I was doing a label classification problem, okay? That would be kind of, I guess, along the lines that we were talking about. And again, when you've got a very small number of labels, okay, you have relatively little information to get doing. If let's say only 1% of the people in the network are terrorists, or hopefully only about 1 out of 1,000 or 1 in 10,000, okay? It's very, very hard to say your neighbors are probably not going to be one. Maybe the neighbors of neighbors, by the time you get a small number of hops, you're to everybody in the universe. And so there are limits to something like that. One of the advantages of the feature this vector feature representation is that it is just better for many machine learning techniques. If you wanted to do a linear regression, what does linear regression take as a feature? It takes a number, okay? Ideally a real number, and ideally a real number that's kind of normally distributed, okay? And saying how many terrorists were there among your neighbors is not as kind of, let's say, robust a feature at capturing this kind of thing. So so I guess what I would say is it produces features. Yes, it's based on connectivity, but it's not just based on on your neighbors. These random walks can get you fairly far along in the graph. How often do random walks take you to a particular neighborhood? That's kind of what's implicitly encoded in here. That might not be coded in a simpler, more explicit feature.
Yeah, basically it's also you capture the pattern that identifies a node, right? And then you try to apply this pattern in other places of the graph, which might be completely disconnected even. Could be even two different clusters, right? So that have actually no connection. But you have the same kind of shape around this node, and the feature vector captures this topological shape, and that's what you can then reuse. It's like if you look at frequent subgraph mining or graph summarization, these are some techniques from graph theory that are kind of have similar focus in identifying repeating patterns in a graph, for instance, or motive finding, something like that.
Right.
Yeah.
I guess another example of that, just because that's a good question, but think back to the similarity between me, who is similar to me in Wikipedia. Now, I am not that big a fish in Wikipedia, okay? And so they're not that. I mean, I'm a good person, but they're not that. There are no explicit links between me and Sergey and Larry, okay, or the people who founded Google. But somehow, in fact, it's not clear there's that many links from my Wikipedia page to any other person's Wikipedia page. Okay, there's probably I haven't looked at it lately, but there's not that many links there. Somehow, if you say, somehow it's capturing something stronger because there are these neighborhood effects. From me, you will get to other computer geeks, and from computer geeks, you're going to get to the people who founded Google or other academic computer scientists and things like that. And that's kind of what is implicitly encoded here. And that's why I think it's a powerful method.
Cool.
That's it.
Sorry.
Sorry.
So how does this technique change? So I'm assuming that most of this has been happening with like single type graphs. So if there are multiple relation types or directed and undirected edges, like how does that change this random walk idea?
Okay. So the So the question has to do with what about when there are different types of graphs? But I think what you're really saying in my speak is that there are different types of edges, okay? And that these edges are labeled and have different kinds of meaning. What do you do to DeepWalk it, okay? Or how do you do to turn that into features? And, so there are a couple of, if you're determined to use, our method, we don't make use of edge labels. So you would have to be judicious in what you are choosing to include as an edge. My recommendation would, first of all, I'd say use everything and see what happens. Then you might find that there are some, depending upon your name, some very common labels that, or edge types that really may not mean very much, okay? There's probably a certain level of judgment of which are the most important relations in capturing it. Maybe you would build a bunch of different representations, one for each edge type. Or group your edge. You still want the graph to be connected, so you need enough density for the graph to be connected. But this is one where, to use our method, I would say you would have to make some kind of a judgment of what you're dealing with. There's been a lot of academic work on these methods since our DeepWalk paper, and many of them try to do different kinds of things where they say, oh, what if it's directed? What if it's what if we have labels? Can we exploit the labels and stuff like that? And so there are variants of this. Again, the key issue is really going to be what kind of a walk do you want to take through the graph? And it might be that some of these edge types are less preferable to walk through than others, okay? And so you might lower the probability or something like that.
Yeah. And in the Neo4j implementation, you can actually project your graph also to any other shape again. So if you have a multi-type graph or multi-label graph, you can also project it to a single label graph if you want to. But I agree, just changing the probability of the walk makes more sense in this. And actually, I think actually a multi-labeled graph has probably better outcomes in DeepWalk than a single-labeled graph because it captures more topological information, basically, because it's richer in its semantics as well.
Right. One of the things, again, when you use these vectors of saying, I say it's 100 dimensions or something like that, this is a parameter you can fix. But that gives you a way to capture similarity that gives you enough space to capture similarity in multiple ways. And so that's why if you've got different edge types, hopefully the embeddings that you learn will capture these different senses of what that thing is in some Gestalt way.
Yeah. Could be actually an interesting thing to run DeepWalk on different of these graph projections, so for each edge type, and then actually compare the similarity of the graphs by comparing the similarity of the features across all nodes. So it would be pairwise comparisons, and then see if you can actually say something about how similar are the graphs at the whole with each other. That could be an interesting thing, and to say how important are these labels on the edges as well. Actually, something we should try out.
Right.
What comes out of
Right.
it? Yeah.
One of the pieces pointed out during the keynote was that Neo4j and property graph databases make it easier to expose how the decisions inside of algorithms like DeepWalk make their correlation and build the vectors up. Is that something that's really easily looked at, either through the Neo4j algorithm or something else, so I can see what are the key pieces that define those pieces of the vector?
I would say that okay, so it has to do a little bit with part of it is a question of interpretability. Okay, how do you interpret these things? And on one level, I would say we are bad for interpretability because, in some sense, we're giving you this point in latent space, and I can't tell you what any of the dimensions mean. On the other hand, one thing that this method is very good at is finding nearest, it naturally lends itself for nearest neighbors. So if you want to ask yourself, oh my God, you have an algorithm for detecting vampires, and you come back and you look and said, Skiena's a vampire? Well, why do I think Skiena's a vampire? And you can look at what other points are near Skiena and start to see, well, see if there was something there that you can learn. So I do think that the fact that you can look at nearest neighbors and nearest points, neighbors in this virtual space, okay? I learn a lot about what the thing is thinking just by looking at those examples. So I don't get explanations of, I made the decision because of this, but I can say, my God, why does it think that this guy looks like that? And when you say, well, his similarities are, he's hanging around with this, if the nearest neighbor of me is Al Capone and somebody like that, you start to understand why you got a view.
Yeah. And for Neo4j itself, what the idea behind the explainability is, for instance, for DeepWalk, you could mark the paths that have been taken and went into a future vector for a node. And then for the actual neural network that computes the word-to-vec frequencies, the idea is there, because it's a neural network, and a neural network is a network as well, so you can actually materialize this as a graph, and then you can actually analyze this neural network with graph methodologies, or you can run graph algorithms on top of it and try to identify which neurons of the neural network are responsible for which decisions, basically. So you can basically try to reverse engineer the decision flow of the neural network, and that's the idea about this kind of explainability of machine learning methods using graph technology. Right? So these two aspects there, and that's something we are looking really forward to explore more and dive into more as well. Cool. Any other questions? Otherwise, thanks so much to Steve for coming and for your presentation. Thank you.
Very good.